Okay, so this is the second part of the talk. In this part, I'm going to present the results that we have obtained regarding the classifications of elliptic Weingarten surfaces and Bernstein problem. And as I said before, this is a joint work with Pablo Mira, José Antonio Galvez, and this is the name of the paper in which you can find the results. So let me recall the basic definitions. So we are dealing with elliptic Weingarten surfaces. These are surfaces with a relation between the principal curvatures that is of elliptic type. This means this condition here. But the way in which we are going to rewrite this condition is this one here. One of the principal curvatures is a strictly decreasing function of the other. And remember that we have two different types. We have elliptic Weingarten surfaces of minimal type if this alpha, the umbilical constant, is 0, and non-minimal type if it is non-zero. And also, let me recall or define a new specific type of elliptic Weingarten surfaces that didn't appear before, and are the uniformly elliptic Weingarten surfaces. So in general, the slope of the curvature diagram is negative, so f is a decreasing function. But when the slope of f is bounded between two negative constants, we say that the surface is not only elliptic, but uniformly elliptic. So if we look at the curvature diagram, the curve where the values of the principal curvatures lie, then this curvature diagram is contained in some wet, okay? So regarding, we were going to focus in the Bernstein problem and the generalized Bernstein problem. So let me start by the Bernstein problem. This is the classification of the elliptic Weingarten entire graphs, and are all of them the planes, or are there non-trivial examples? So, well, the first remark that we saw in the first part of the talk is that we can't restrict ourselves to the minimal case because the non-minimal is trivial. This is just a easy consequence of the maximum principle. And the second remark is that in the uniformly elliptic case, the Bernstein problem is known to be solved, is true, okay? And the proof is quite short and is the following. First, we can assume that the surface is of minimal type because the non-minimal type is trivial. So this means that the curvature diagram actually starts here in the origin, and the surface is uniformly elliptic, so it's contained in some wet. And under these conditions, it can be proved that such a surface must have quasi-conformal Gauss map, okay? I'm not going to enter into details about what quasi-conformal means right now, but this is something related to what happens in the case of minimal surfaces, mean curvature zero surfaces. It's very well known that minimal surfaces have a conformal Gauss map, okay? So this is a weaker condition. Uniformly elliptic Weingarten surfaces of minimal type, this only works for minimal type, have quasi-conformal Gauss map. And then there is a very deep result by Simon in late 70s that says that if an entire graph has quasi-conformal Gauss map, then it has to be a plane. So using this result, the Bernstein problem is solved in the uniformly elliptic case, which is a particular case of our problem. And finally, the last remark before stating our results is regarding the behavior of the function f, this function f that gives you the Weingarten equation, okay? So we have three possibilities for the behavior of the function f. Either f is not bounded at infinity, or f has some horizontal asymptote and is defined up to infinity but is bounded, or F has some vertical asymptote, okay? Recall that F is a strictly decreasing function. So actually, up to reversing the orientation, these two cases we have here, this and this, are equivalent. So if we change the orientation, then we go to the other case. So up to reversing the orientation, we are going to assume that we only have two possibilities. Either F is bounded at infinity or F is not bounded at infinity. Okay, and observe that the uniformly elliptic case is of this type. F is not bounded at infinity. Okay, so our contribution to the Bernstein problem is this theorem that you have here. In the case where F is bounded at infinity, then you can answer affirmatively the question we posed. So planes are the only elliptic Weingarten entire graphs when the F is bounded at infinity. So the case where F is not bounded but not uniformly elliptic, so F prime goes to 0 or to minus infinity at infinity, this case is the one that remains open after this theorem. Okay. And this is our contribution regarding the Bernstein problem. Regarding the generalized Bernstein problem, that is the classification of the elliptic Weingarten complete multigraphs, we have these two theorems here. First theorem is that in the uniformly elliptic case, the answer is yes, okay. And when the function f defining the Weingarten equation is not bounded and the surface is of minimal type, then we can also solve the problem. Okay, so in this case, what remains open is the case where the surface, the function f is bounded at infinity but of non-minimal type, or when the function f is not bounded at infinity but not uniformly elliptic. Okay, so these are just partial solutions to the generalized Bernstein problem in these two situations. Okay, so if we put the three results together, you can actually see that theorem 1, the one regarding the Bernstein problem, is actually a consequence of the last result, because an entire graph is in particular a complete multigraph. So actually theorem 1 is a consequence of theorem B. Okay, so these are the two main results of the talk, and the other one is a straightforward consequence. And these two results are based on this main lemma that I'm going to state here that we prove, and it has nothing to do with Weingarten surfaces. Actually, it is for surfaces with quasi-conformal Gauss map. Okay, so I'm not going to prove the main lemma right now. I will leave the proof for the final part of the talk. And I'm going to sketch now the proofs of theorem A and theorem B, assuming the main lemma, okay? So this is theorem A, okay? Planes are the only uniformly elliptic complete multigraphs, okay? So if my function f is uniformly elliptic, then the only possibility is the plane. So the proof of theorem A is has two steps, okay? In the first step, we are going to prove what is called curvature estimates for our surfaces. Curvature estimates is to prove that the second fundamental form is bounded. So the principal curvatures are bounded, okay? And to do so, we follow an approach, an argument by Rosenberg, Suam, and Tubiana for CMC surfaces in Riemannian three-manifold, stable CMC surfaces in Riemannian three-manifolds. And the process, the idea is, okay, so reasoning by contradiction, assume that your surface has unbounded second fundamental form. So you can take small disks on your surface in which the second fundamental form is getting bigger and bigger and bigger. Now you rescale these disks so that the second fundamental form now is bounded after the rescaling. And now you have a sequence of these rescale disks. So in the CMC case, you can prove that this sequence converges to a minimal surface. Okay. The main difficulty for us in our case is that even though if you are able to prove that this limit sequence converges to something, you cannot assure that what you get in the limit is going to be a Weingarten surface, because your equation, your differential equation, can be lost in the limit. So you cannot control that the sequence of partial differential equations that you have is going to converge to something nice. Okay, so this is the main difficulty that arises in this case when you compare with the constant mean curvature setting. Okay, so in this case, what we can prove is that we converge to something, and this something is a multigraph with bounded second fundamental form, and it is maybe not a Weingarten surface, but it has quasi-conformal Gauss map. Okay, so in order to do this, we use the uniform ellipticity condition and a result by Nirenberg regarding fully nonlinear PDEs in two variables. Okay, so after this blow-up process, this rescaling process, we have a limit surface. But now we remember our main lemma. A surface that is a complete multigraph with bounded second fundamental form and quasi-conformal Gauss map has to be a plane. And this is a contradiction because our limit surface was not a plane. Okay, so this is how, more or less in a very sketch way, we prove that our surface has bounded second fundamental form, bounded principal curvatures. And now step 2 is to prove that planes are the only elliptic complete multigraphs with bounded second fundamental form. Okay, and in this case, if your surface is of minimal type, then this is straightforward because the Gauss map is going to be conformal and you can use the main lemma to prove that it has to be a plane. If your surface is of non-minimal type, then you have to work a little bit more. And what we do is that first we control the asymptotic behavior. We prove that at infinity our surface is asymptotic to a cylinder in some way. And then we use a perturbation argument to obtain a contradiction. Okay, so this case is not possible, the non-minimal one. So the only possibility is the minimal one, so our surface is a plane. Okay, and this is more or less the sketch of the proof of theorem A. Theorem B is that planes are the only elliptic Weingarten complete multigraphs of minimal type and with bounded f. Okay, f is the function defining the Weingarten relation. So remember that we have two different behaviors up to reversing the orientation, two different behaviors for the function f, either it is bounded at infinity or it is not. So we are in this case here, okay? We are working in this second case, and our surface is of minimal type. So the curvature diagram starts here at the origin. So in this case, to prove theorem B, the idea is to prove that thanks to this condition that f is bounded at infinity, you can find a suitable T0 for which the parallel surface satisfies these three conditions here. Okay, so the parallel surface is regular because in general when you do a parallel surface to a given one, singularities can appear. So if you choose T0 carefully, then the parallel surface is going to be regular, is going to be a complete multigraph, it's going to have bounded second fundamental form. This is because of the relation that you have between the principal curvatures of the parallel surface and the original one. And the main point is that the Gauss map of the parallel surface is going to be conformal. And then you use our main lemma again to prove that the parallel surface has to be a plane. But if the parallel surface is a plane, your original surface is also a plane, and you are done. Okay, so this is how we prove theorems A and B, assuming the main lemma. Now, in the final part of the talk, I'm going to sketch the proof of the main lemma, and I'm going to explain some facts about quasi-conformal Gauss maps.